Okay, now I've sketched the V, W, and U vectors, but now I've done it in the context of a Cartesian coordinate system, because these are vectors in the plane. Well, I can throw a Cartesian coordinate system in here. And the Cartesian coordinate system doesn't necessarily have to be vertical and horizontal. It could be rotated, tilted, any way. And you want to kind of keep that in mind, but for right now, we'll draw the coordinate system in the usual manner. So, I want to be able to put numbers on V, W, and U. The X and Y axes here have been marked off with reasonably equal scales. So let's say this is a unit. In other words, this is 1 and this is 1. I can put numbers on this vector, and the numbers will just be how far we have to go from here to here, and then how far from here to here if we move first parallel to the x-axis, then parallel to the y-axis. So how far do we have to move parallel to the x-axis? This far. That looks like 3 units. So we got to go 3 units, and it's in the positive direction, so it'll be a plus 3 in the x direction. Now I'm not going to write out that qualifier. Okay, how far in the y direction? Looks like about 3 in the y direction. Okay, so we're going to say the vector v is the vector 3, 3. And I will use this is basically a kind of elongated less than or greater than sign. It's like I'm going to call them pointy parentheses. Now, the Larson text uses parentheses, and there's good reason for that. You want to identify the vector space as a set of ordered pairs, and you use ordered pairs use parentheses to represent ordered pairs. However, you also use parentheses to represent points in the plane, and it's a little confusing at first if you use the same notation for points in the plane as you use for vectors. A vector is something that takes you from one point to another, and you can move it anywhere you want to, so it doesn't always move from the same point to the same point. Okay? If you know the point where the vector starts, then these numbers tell you how far you got to go in each direction to get to the point where it stops, to its terminal point. Okay, so there's a vector v, and I'm going to use these pointy parentheses, okay? W, what do you think the components of W are? Well, you know, we've got to go down some, we got to go over some. It looks like how far we got to go over. That looks like, I'm going to say that's about 0.7 units, okay? And of course we do the component in the x direction first, just like we would with an ordered pair, x then y, okay? So the run, the change in the x direction is 0.7. The rise, change in the y direction, looks like it's maybe 1.5. Now, I'm not sure that's a very accurate representation, but that's what we're going to assume, okay? U, what's the U vector? Well, the way the U vector is drawn, it goes over just a little bit in the x direction, and it goes up quite a bit in the y direction, okay? So let's see, if a unit is this big, that looks like about 0.4 in the x direction, and then it looks like we go about 3 in the y direction. I'll just say 0.4, 3. So, these are the displacement coordinates of the vector, okay? Might not use that term, displacement coordinates. These are the components of the vector. Now let's see, if we apply W, or apply V, starting at the point, oh, let's just pick a good point. Let's pick the point 2, now let's go 3, and 1, 2, 3, 4, 5, 6, 7, 3, 7. So now here's the point 3, 7, and I'm using regular old parentheses to indicate the point in the plane. And then we apply the vector v. Where's the terminal point of v? Well, where do you think? V moves you 3 units in the x direction and 3 units in the y direction. So we're going to move over 3 units here. We're going to move up 3 units. We started at 3, 7. We move over 3. So our x coordinate is going to have to go from 3 to 6. And our y coordinate, which was 7, is going to have to go up by 3. That's going to give us 10. So we end up at the point 6, 10. Okay. Now there's another way to look at this whole thing. Let's just draw another coordinate system here. And let's say here's our point 3, 7. And let's do a vector from the origin out to the point 3, 7. Okay, so this is the vector 3, 7. And to that we add the vector v. And of course the vector v is the vector with components 3, 3. That looks like a 37 or something, but let's just make it a little bigger. Okay? Now, the resultant is a vector from the origin up to this point. And this is the vector 3, 7 plus the vector 3, 3. That equals the vector, well, let's just write it out. 3 plus 3, 7 plus 3, which is the vector 3, 10. And that vector starts at the origin and ends at this point, meaning that this point must be the point 3, 10. So and this point, of course, is the point 3, 7. So that depicts your displacement from 3, 7 to 6, 10 as a sum of a vector from the origin to the point 3, 7 added to the vector v, which has components 3, 3. So it's the vector 3, 7, which takes you from the origin to 3, 7, added to the vector 3, 3, takes you from the origin to the point 3, 10. So that this point is 3, 10.